Welcome to Superheroes of Science. I'm Steven.
And I'm Sarah. We co-host Science from the Experts. Our guests are professionals doing cutting-edge science right now.
They're experts in their field discussing what they know best. So listen up and learn real science from real people.
Subscribe now and stay informed of our latest episodes and show your support. Joining us today on Superheroes of Science, we are so excited to welcome Michael Kirk. Michael is a research scientist with the NASA Goddard Space Flight Center and is the PI of NASA HEAT. So what is NASA HEAT?
Well, hello, everyone. I'm really excited to be here, first and foremost. I am excited to talk to you today about heliophysics, about the sun-Earth connection. But to start off with, NASA HEAT is the Heliophysics Education Activation Team. What that means is that we're coming out to you in both formal and informal education settings and talking to you about the sun and about how the sun and Earth work together.
But what is heliophysics?
Yeah.
Okay. We're going to get into the meat of it right now, aren't we? Heliophysics. Okay. So heliophysics is it's two words, and we took them and we took two words and put them together. So helio means sun, and physics, of course, is the explaining of how things work and behave in our universe. So when you stick them together, you get the way the sun works and the way the sun behaves in our universe. And the idea of heliophysics is actually, it's a relatively new idea. It didn't really exist that long ago. I mean, just 20 years ago, this word heliophysics didn't even exist. So this is a relatively new word. But what we're trying to do by using the word heliophysics is capture this idea that the sun isn't just something that rises in the morning and sets at night, but actually affects our lives every day and is also a fundamental laboratory for plasma physics. So when you're studying how hot temperatures, hot gases under pressure with magnetic fields, how they behave, you can either go to some sophisticated laboratory here on Earth that takes millions of dollars to run and years to build, or you can get a telescope and point it at the sun and see those same effects: high temperature, high pressure, plasma. And that is what heliophysics is. It's about the relationship between the Earth and the sun and about the physics of how the sun actually works.
You might be annoyed at me, or both of you might be, when I start asking, you said studying plasma. So is the sun a plasmic state?
It is. So I think there was a song by They Might Be Giants. I don't know if anybody's a fan of them. So they put out they made a song that says, like, the sun is a massive incandescent gas. Okay, so that is actually not technically true. And so they came out with another song years later called The Sun is a Miasma of Plasma. Super catchy. Go look it up. A lot of fun. So what is a plasma? A plasma is the fourth state of matter. Okay, so you have a solid, and then you start heating a solid up, and the solid melts. It doesn't matter if it's ice or if it's metal. The solid will melt and turn into a liquid. Okay, and you still keep on dumping heat into it, and the liquid will eventually evaporate and turn into a gas. Okay, so that's a third state of matter. We have them a lot here on Earth. You're very used to it. Now, if you keep on heating the gas even hotter, then what ends up happening is those molecules that form the gas end up starting to break apart, and you get ions. So let's say you have hydrogen, the simplest atom there is, one proton, one electron. When you start heating hydrogen up even further, the electron and proton separate from each other. At that point, you don't really have hydrogen anymore. You just have a soup of charged particles. That is a plasma. And so you can talk about different types of plasmas. You can talk about partially ionized plasmas where only some of the atoms have broken apart, or fully ionized plasmas where actually you have just a complete soup of electrons and protons. But that is the state of matter that we call a plasma, and that our sun exists in. And you get that from extremely high temperatures or extremely high pressures. The sun has both.
I think that's the best explanation of plasma as a state of matter that I've ever heard. And I really appreciate it. Like, that made a lot of sense.
Good. I understood it. So it made sense to me. So it must have been a good explanation. but I don't know. I guess I didn't realize it was a a big ball of plasma.
Yeah.
And so that threw me off just a little bit there.
Mhm.
Huh. It emits a lot of energy, right?
Oh
It-
yeah.
what-
So so the sun is the source of almost all of our energy on Earth and in our solar system. And I say almost because if you're going to technically count up all the energy, there is some energy left over from the formation of the Earth that is, built into uranium and nuclear power. Some that's built into the magnetic fields of the Earth. So there's certainly some there. But on the surface of the Earth, most or almost all of our energy comes from the sun. And this is all of our energy. This is not just, the sunlight that hits you in the face when you walk outside, or the solar panels that are going to charge your car or your house, but also if you're talking about fossil fuels too, all of those come from plants and some animals, but mostly plants that have sat underground under heat and pressure for years and turned into oil, crude oil, and then we take it and refine it and make different products out of it. But all of those plants got their energy from the sun. So it really, almost everything that we do here on Earth is somehow connected back to the sun, and all of our energy that we use on a daily basis is solar power in one way or another. And this is a good thing. And we happen to live in a place where the Earth is just the right distance away from the sun to make us warm but not hot, not too cold but not too hot. Just it's called the habitable zone. When you're looking at extra solar planets outside of the solar system, that's what they're looking for if you're going to find life, because it is the universe is a very cold place most of the time, or you're close to the sun, it's way too hot. So the fact that we live right here, we just get the right amount of energy coming from the sun, and the sun is fairly constant with that. Year in, year out, millennia in, millennia out, we get a very consistent amount of energy coming from the sun, which makes it habitable. It makes it so that we and the rest of life can exist here on Earth.
Mhm.
But other than helping plants grow and everything on Earth live, um, what does it do? What does it? I mean, there's things it does to our atmosphere and stuff. Then, with all that energy being bombarded on us,
Yeah.
what kinds of things
Yeah.
is it doing to our planet?
That's a fantastic question, because you actually so I was a little careful with the words I chose, because the sun is mostly constant, but not completely stable. So every once in a while, the sun will go through an active cycle and then a quiet cycle. And what that means is, when the sun is active, it means there's lots of explosions and eruptions on the sun. We call these solar flares or coronal mass ejections, where the solar flare releases a bunch of energy into the atmosphere or into the universe. And then the coronal mass ejection actually pushes out a big cloud of plasma, magnetic fields and particles out into space. Okay, fortunately, we're pretty lucky here on Earth also, because we have A, an atmosphere, and B, a magnetic field. Okay, both of those protect us from almost all effects from both of those events. So if a big flare happens on the sun and a bunch of radiation comes charging towards the Earth, the atmosphere is going to absorb most of that and then irradiate it away, and we're going to be fine. Okay, a coronal mass ejection, a CME, comes rushing from the sun, hits the Earth. The magnetic fields, they're going to take care of most of that, and they're going to funnel it down to North Pole and the South Pole of the Earth. And actually, we see those as aurora when that happens. When those CMEs get redirected and they hit the Earth's upper atmosphere, it's the Northern Lights or the Southern Lights. Pretty cool. But the real challenge is, we as humans, we don't like to stay put, right? We're kind of pushing out into space deeper and deeper, either with satellites or with human exploration. Well, once you get outside of the Earth's protective atmosphere and protective magnetic fields, whoa, well, now you're very susceptible to these things.
Mhm.
So when you're designing a satellite, if you are an aerospace engineer and designing a satellite to be in orbit for a long period of time, the radiation effects from the sun are something you have to take into account very carefully. But also, you have to take into account the atmospheric effects, because if you remember thinking about gases and energies, we talked about this a little earlier. If you put a bunch of energy into a gas, it'll puff up and it'll expand. And so the Earth's atmosphere does the same thing. And so if you have a satellite in orbit and a bunch of energy gets dumped into the Earth's atmosphere by the sun, solar activity, then the Earth's atmosphere will expand and the satellite will experience more drag, which means that it's going to last less time. It's going to deorbit. It's going to fall back into Earth a whole lot quicker. So this idea of the solar activity is critical when you're talking about sending anything into space. You got to be very careful about knowing what the sun's going to do, making predictions, and then making very carefully calculated equations to compensate for those things as you come in. So like more rocket fuel, for example, to boost your altitude a little bit. But fortunately for us, the sun goes through a cycle. It's called the solar cycle. So every about 11 to 12 years, we go through a period of quiet time and then active time and then quiet time. Right now, we're ramping up towards solar maximum. So the sun's getting more and more active. It'll reach solar maximum probably around 2024. That's still a little iffy. We have forecast models, but they're not always 100% accurate. So we're looking about 2024 for solar maximum, and then it will ramp down to solar minimum, where the sun becomes very quiet, very stable again.
What?
I know. There's a lot of questions.
Are you wanting?
Oh, you go ahead.
Okay.
I think.
So what's causing these solar cycles?
Ooh.
We do like amateur radio, and that's all they talk about is solar cycles. And so 2 questions. Can I ask two?
Ask you.
I'm sorry, I don't mean to hog.
No, yeah.
1, what causes the solar cycles? And 2, why are all these amateur radio people talking about them? So obviously it's doing something to our ionosphere, our atmosphere here. And so why is that important for people to know?
Yeah. Okay. So I'll start off with the easy question, which is your second one. So when the sun has a lot of activity, there's a lot of solar flares. The ionosphere is full of ions. It's actually a state of plasma, right? Okay. So we have plasma.
Don't run past that. Wait. The ionosphere on Earth is plasmic?
So it has plasmic properties to it because it is a soup of ions. So it's not fully ionized, right? So it's not like the sun, and because we're not talking about millions of degrees here, but there's enough energy dumped into the ionosphere to make a soup of ions. So no longer is it just a gas anymore. It has these special properties that are plasmic. It has plasmic properties.
Huh.
Yeah.
That's really cool. I didn't know.
Sorry.
No, it's fine.
Interrupt your explanation.
Okay. So getting back to the ionosphere. Okay, so in the ionosphere, when you dump a bunch of energy into the ionosphere, and it expands, like any sort of particles, you heat them up and they move around more and they're going to take up more volume. What's really interesting about this is that it changes the way radio communications can work here on Earth. So a lot of times with ham radios and other ground-based radio systems, they end up bouncing signals off of the underside of the ionosphere. So when the atmosphere starts going from a gas to a little bit more ionized and stops behaving quite the same, you can actually you can bounce radio signals off of that. And so you can get these radio signals traveling great distances depending on the condition of the ionosphere. This has been well known for years and years. I mean, I think there's a couple of interesting anecdotes about, let's see here. I want to say it was the Vietnam War. There was a bunch of mines, sea mines, that accidentally exploded because they got a spurious radio signal because of solar activity. So there's some really cool examples in the past of how these radio signals really mess things up. Or I think there's other anecdotes about World War II and critical radio signals being lost because of the ionosphere changing, and they weren't ready for it. They couldn't compensate for it, and so they just the radio signals didn't get out to the front lines. So there's some interesting examples from wartime, but in just everyday life, the changing state of the ionosphere can change any signal coming through it from space. So let's say that you have, I have one right here. I bet you have one too. I have a phone, right? I have an iPhone here. Okay. In the iPhone, there's a GPS receiver. Okay, so GPS receivers work by getting a signal from a satellite that comes down, and actually they look at 4 or 5 different satellites. It triangulates the point and it says you're right here on the Earth, and can give you an accurate location of where you are on the planet. And then you can, get directions to the grocery store, whatever you're trying to do. But you're using these signals coming in from outer space in order to get you to your friend's house or the grocery store. However, if the ionosphere puffs up and changes from a lot of this solar activity, those signals can get diverted. They can get sort of it's called GPS scintillation. They can change a bit, and so that accuracy can completely get destroyed. So if you get lost using your GPS one time, like it says you're 5 streets over that way, and you're actually right here, and you take the wrong turn and all of that, it could be because of a solar storm. Not because your GPS is somehow faulty. It's just the signals from those satellites are getting scrambled.
That's really interesting. Yeah.
So, okay, so now going back to the other question, which was about the solar cycle. Okay, this is a little bit more complicated. This is a lot harder because I'll just come out front. We're all adults here. We don't really know. I mean, we have ideas. Don't get me wrong. There's a lot of people studying, a lot of very smart people studying it, a lot smarter than I am. But when it comes down to it, we don't really know. And the reason why we don't know is that we really only have very limited information about how our sun works. Okay, so let me just paint the picture for you. First of all, we're talking about these 11 or 12-year cycles. So in the solar cycle, what ends up happening is the pole of the sun flips. Okay, so every 11 years, what that means is that the sun has a north pole and a south pole, magnetic poles, sort of like Earth, kind of like you have a north pole and a south pole, kind of like a bar magnet. And then during that solar cycle, they flip. The north becomes the south, and the south becomes the north, and it flips. Okay, and then 12 years later, ish, 13 years later, it flips back again, and it's been doing that. So we first noticed this as human society not that long ago, considering. I think it was back in the 1700s, we've started recording what's called the sunspot cycle. So these are small blemishes that you see on the surface of the sun that are actually strong magnetic fields. So these are really strong magnetic fields that block out some of the radiation coming from the sun. They look like dark spots. Back in the 1700s, I started keeping a log of all these spots and where they exist. And so we have a log of when the activity goes up, there's more sunspots. And when the activity comes back down, there's less sunspots. We've been recording it, and we've had a pretty good record. I mean, we have, several dozen of these. Well, several dozen, that's not a very good sample size, is it? I mean, we just haven't seen the sun for that long. I mean, the sun is what 3.5 billion, 4 billion years old, 0.8 billion years old. We haven't seen enough of the sun to really understand why it's doing what it's doing. Okay, so that's one problem. We just haven't been around long enough to observe it. The second problem is that nearly all of our views of the sun are from Earth. We have observatories that observe the sun on Earth. We put up satellites, but most of them are going around Earth, or they're somewhere close to Earth looking at the sun. There have been a few satellites that go around on the backside of the sun and come out again, but those are pretty few and far between. There's not many of them. I think right now I can think of 4 that are in orbit right now. So we don't normally see much of the sun besides the Earth's facing side. And we've actually never seen the poles of the sun directly. So we've never actually flown up to see the North Pole or the South Pole of the sun. So part of the reason that it's so hard to understand something about these solar cycles, these magnetic cycles of the sun where the North Pole and the South Pole flips, is that we just haven't seen enough of it. We haven't seen the North Pole of the sun. We haven't seen the backside of the sun consistently. We haven't observed the sun for 1,000 years to be able to track and figure out how all this works. The more subtle answer to all of that is that it's the interior processes of the sun that drive the solar cycle. So there are really significant energy motions from moving energy from the core of the sun, where the energy is made, out to the outer atmosphere, and through convection and radiation and magnetic fields. It's a very dense and complicated process. And the computer models that we have of it, the simulations of the sun we have of it, just haven't been able to reproduce exactly what we've seen on the sun yet. We're getting there, but we just don't quite know yet.
Now, I don't remember if I've heard this somewhere. Is the sun itself like rotating or moving, or is the sun kind of like how the Earth rotates? Does the sun rotate?
Yeah, it does, but not exactly like the Earth rotates.
Okay.
So the sun is a big miasma of plasma, as we talked about earlier, right? Okay,
Right.
so it doesn't actually have like a hard surface like the Earth does. It doesn't have a rocky surface that you could stand on. It just gets more and more dense as you go in, and so it's like it's the consistency of pudding, and then it's the consistency of concrete, and then it's the consistency of steel, and then the density just slowly gets more and more dense. So because of that, when the sun spins, it doesn't rotate like a top, like a rigid body. It does what we call differential rotation, which means that the equator rotates at a different speed than the pole does. And so things tend to get smeared out. Jupiter acts the same way. It's a big gas giant planet. It spins the same way. And in fact, the atmosphere here on Earth, it has similar sorts of effects. There are other things going on with the Earth, so I'm not an expert in that, so we won't go into it. But whenever you have like a big ball of gas moving, you get this differential rotation where you get the different latitudes spinning at different rates. And so, like, for example, the equator goes around about once every 25 days. Versus the poles go around once every 28, 29 days. So it just depends on where you look. We call a Carrington rotation is the term that scientists use to describe the one rotation of the sun. Well, it's really just an average rotation of the sun. And so you get these, if you make a map of the sun, you get these weird smearing effects at the poles or something like that, because it doesn't actually rotate nice and easy. So it's one of those challenges whenever you're studying the sun.
Very cool. Now, you had mentioned space forecasts or not forecasts, solar forecasts. So who are the forecasts?
Is there a National Solar Forecast Center, like
Yeah.
National Weather Center?
like the National Weather Service? And who should be interested in solar forecasts? Or who will these affect? Or who is watching for them?
Well, I think everybody should be interested, but
Right,
I might be biased.
Of course.
You're not his.
Of course.
I know.
So they're really here in the U.S. There are really three different groups that do solar forecasts. So where I work at NASA, we have the Community Coordinated Modeling Center, and what that is a group that pulls together the scientific models for how the sun behaves, or forecasts for how eruptions should travel through space, or any of these specific forecasts, and pulls them all together into a public resource. Yeah, I mean, you can go check it out, the CCMC, and you can look at these models and see what the forecasts are. Okay, that's a much research oriented. If you want, like, should I launch my satellite today forecasts, then you're going to go to NOAA, the National Oceanic and Atmosphere Association. So if you go to NOAA, NOAA has a Space Weather Prediction Center. Space Weather Prediction Center handles those forecasts, including the all clear forecast saying, yes, please launch your satellite or spacecraft today, or the forecast for there's a 30% chance of a medium-sized flare or a large-sized flare. So they are the ones that really handle those day-to-day forecasts. It's fun. You can go check it out because they will tell you, there's a high chance or high probability of a solar storm, and if you live at a northern latitude, you might be able to see some northern lights out of it, which would be cool. So especially like, yeah, if you're in Michigan or Minnesota or Wisconsin or North Dakota, they see northern lights all the time. And then, of course, then there's the military side of things, and the Air Force Research Lab does its own forecast for military applications. Of course, we all sort of work together, but the military is, like I was mentioning earlier, that there's been some issues during wartime that, you know, a message didn't get conveyed, or that a munition was detonated prematurely because of solar activity. The military recognized this back in the 40s and 50s, and so they're very interested in having a very accurate forecast for all of the activities they're doing. So they do their own forecasting. Of course, you can see some of these models that the Air Force uses, or that NOAA uses, at the Community Coordinated Modeling Center at NASA. So you can go and see it for yourself. So a lot of these models are public source, and you can go and look at them if you want.
That's cool.
Yeah, that is really, it's good to know. I mean, it's neat to know just there are places you could go to check it out. I know when I was younger, we live here kind of central Indiana, but we were really interested. We would love to see the Northern Lights. And I remember my dad would look at some things and he'd say, oh, you know, there might be a chance if we go out somewhere where it's really dark, but it was like only certain times. I never understood as a kid where those chances might be coming from, but that makes sense now to hear about these solar storms.
Yeah. Well, not only that, so you want a clear skies, of course, no clouds.
Mm-hmm.
Because if you're chasing aurora, you don't want clouds in your way. And then oftentimes people associate aurora with wintertime. And that's really because it's darkness. I mean, if it's dark out, you have a better chance of seeing it. You have a more nighttime. You have the more opportunities to see it. So yes, aurora happen all year long, but in the northern winter, you have a lot of darkness, and you can actually have a better chance of seeing it. So we're coming up to a very good aurora watching season, right? So it's going to be winter. The sun's becoming more active. So, you know, keep your eye on those forecasts, because I think there's going to be some good aurora coming up.
Oh, that's awesome.
Oh, that's cool.
Yeah.
Now, one of the things we wanted to ask about eclipse, right?
Yeah.
That's
yeah.
one of the things.
Mhm.
One of I thought so. I don't know if I don't know if we've asked you anything that we said we were going to ask you yet, or that we didn't say we was going to ask you. We're pretty random, but I know that we're going to have a solar eclipse here that Indiana actually will be in like full view of, which I don't ever remember that happening in my lifetime.
Right.
I'm really curious about this. A, why hasn't it happened here in my lifetime? And B, what is it?
All right. We'll start again
Stop
with
the
your second question
two-part
first.
questions.
Yeah. So what is a total solar eclipse? A total solar eclipse happens when the moon blocks out the sun completely, and actually it just casts a shadow onto the earth. So, you know, you have the sun, you have the earth, and then the moon just passes between the two and casts a small little shadow on the earth. And we live in a really interesting place in the entire solar system, because this is the only place where our moon, the moon here on Earth, exactly blocks out the sun. Like, it exactly covers it, or maybe just a little extra covers it. It doesn't happen anywhere else. Like any other planet that you're on, it doesn't happen the same way. So it makes us special here. And then even more special is that path of totality, where the sun is completely blocked by the moon. It's fairly narrow. You're only talking, well, it depends on the eclipse how fat the line is, but you're talking maybe 50 to 100 miles in a normal eclipse. And so at that point where you're sitting on the line of totality, so the sun is completely blocked by the moon, then what happens is you can see this outer edge of the sun that normally is invisible to us because the sun's too bright, called the corona. This is where all the space weather happens that we were talking about earlier. Okay, so this is where all of those flares and coronal mass ejections, all of that stuff, this is where it comes from, is in the solar corona right here. And so you can see it with your own eyes. Like the bright disk of the sun is covered up, and you can see this kind of gossamer thin. It's really striking. It's absolutely gorgeous. I was able to see it in 2017 in Oregon, and it was absolutely spectacular. It's one of those events that lives up to the hype, right? Okay, so there are other events in astronomy. Like, I love astronomy, but there are other events where, you go out and see a meteor shower, and by the time you've seen the fourth shooting star, you're like, oh, that was really nice. And then you stick around for another hour and you see the 100th shooting star, and you're like, wow, that was really nice. And it was a pleasant evening. This is like, I don't know, 1,000 times cooler than that, maybe 1,000,000 times cooler than that. Okay. It only lasts for a few minutes. I'd have to look up exactly, depending on where you are in Indiana, you're going to get a different amount, but it's going to go, the eclipse in 2024, it's going to start in Mexico, come on shore in about Mazatlan, Mexico, come up through Texas, hitting some Oklahoma, Arkansas, Indiana, Ohio, and then up the Great Lakes, hitting the, let's see here, Lake Erie, and then out the St. Lawrence Seaway, sort of New Brunswick area up through Canada. So it kind of cuts across the heartland of the United States, and it's going to provide 35 million people the opportunity to see a total solar eclipse without moving. You don't have to travel anywhere. You just go outside at the right time and you can see it. Okay. April 8th, 2024, put it on your calendar now, circle it, highlight it, set yourself a reminder on your phone, do whatever you can. Remember to go outside and see this. This is absolutely spectacular. And the reason why is that if you stand in any one location on the Earth, they're pretty rare. Like, you just are not going to see them very often because the moon's shadow is kind of small compared to the Earth. It's a pretty small shadow. So if you were to just stand someplace and wait for a solar eclipse, you'd be waiting on average about 300 to 350 years before seeing one. So if you just were say, stand here, I'm going to look up and wait for a total solar eclipse, it's 300, 350 years. So it seems like a very rare event, but if you look at the entire Earth, it's actually much more common. We see a solar eclipse about once or twice a year on average.
Oh, wow.
However, the Earth is mostly covered by water. It's mostly remote. There's not a lot of people living in a lot of places. And so there are people that literally travel around the world looking for total solar eclipses. They chase them around the world. And so I can guarantee in your backyard, there will be people from around the world that will travel to Indiana or wherever you live in order to see the solar eclipse. That's how big it is. In Oregon in 2017, we had tourists from Japan and from Australia fly to Oregon just to see the eclipse, just for the 2 minutes to glimpse the view of the solar corona. That's how spectacular it is.
But what are they using to look? Because I know you can't look right at it still, right?
Okay. Most of the time, yes. I would say anytime when you look at the sun, you need to use a solar filter or solar eclipse glasses. You have to have special filters and special glasses. The only exception ever is when you're in totality. When the sun is completely covered, then you can remove your eclipse glasses. You can take the filter off your camera and actually take a picture or look at it directly. That is the only time. Every other time when the sun is almost covered, you can't do it. When the sun is like 99.99% covered, you still can't do it. Only when it's 100% covered can you take off those filters and actually see it with your own eyes. And it is absolutely gorgeous. So please do, because if you forget to take them off, you're going to miss the best part.
Oh, I didn't know we could do that. Wow.
It sounds a little risky though. Like, I'm just thinking, okay, but like, what if I take them off and it's 99.9?
That's a good question. How do you know it's 100%?
Okay, so if you go to NASA's Eclipse website, let's see here, Eclipse, solarsystem.nasa.gov/eclipses. We're going to get a simpler web address once everything is getting ramping up. But go to NASA's Eclipse website, or there's many other Eclipse websites out there. They will give you a forecast down to probably the second of when the eclipse will happen right where you are. So that's going to help. Okay, number two, when you have your eclipse glasses on, you're looking up at the sun. When it's totally covered, everything's black. You're not going to see anything anymore. So then you know it's safe to take them off, right? Okay. And so if you're watching an eclipse, what we did is we knew the eclipse was going to last, let's say 3 minutes and 32 seconds. Okay. So I got out my phone and set a timer for 3 minutes and 30 seconds and press go as soon as I took off my glasses. Timer goes off, you put your glasses on, or you just look away. It's not not like it's going to blind everything. You just don't look at the sun anymore. And then it comes back into the sun comes out of totality, and then you put your glasses back on, you can look back up again. So it's really not that scary. The worst that would happen is that you're staring at the sun. It's sort of like walking out of a dark room into a bright day, where you're like, "Whoa, that's too bright," and you look away. And so as long as you don't force yourself to look at the sun, you'll be okay. You'll be fine. If you force yourself, like you're trying to prove something, then it can cause some real damage. So please don't do that.
That's very reassuring. I feel more confident about viewing this now. So that's awesome.
Well, I'll have my camera ready.
Yeah.
Now.
Yeah.
So if you are thinking about taking photos of this, which is super exciting, if you want to, please do. But also don't feel obligated. There are so many professional photographers out there that will probably be near you or in your backyard that will take amazing photos of the eclipse because they're used to it. They got the, all of their camera settings right. They have the tripods. They have everything just set up perfectly. Maybe take a snapshot, but don't, unless this is a hobby of yours and you're super excited to do it, just experience it, just enjoy it, because it's so much better to just experience it and look at it. Maybe take a snapshot of you and your friend in totality, but don't pressure yourself too much to get the perfect shot, because there will be tons of beautiful shots coming out afterwards.
That's really cool.
That is cool.
Yeah.
I like that. Now the center, I know you probably expected us to talk about that mostly, but we haven't even got to that. The center, the what'd you call it, is heat.
NASA heat.
And what is this center for?
Yeah. So what we're the Heliophysics Education Activation Team. It's NASA. We like our acronyms. So NASA heat. We're the sun. So this group, we are tasked with getting heliophysics, the idea of the sun and the sun-Earth relation, into schools, into after-school clubs, into any place that somebody is interested in learning more about the sun. And the really neat thing is that the sun has so many different science lessons that are just ripe for addition into any sort of curriculum. So if you are teaching about colors, well, the sunlight has all the colors in it. You can get out a prism and break the sunlight into the colors. If you're talking about, I don't know, Earth's energy budget, about the energy coming in and how it gets just reflected off the different surfaces on the Earth and what gets trapped and all of that, the energy comes from the sun, and understanding that solar energy is the first part of that. But even really interesting things, like if you're teaching math and you want to understand, or you want to give a good context to calculus problems that you're trying to teach, or algebra or geometry, any of these fundamental math or science topics, the sun has ready-made problems for you. So maybe you're trying to teach geometry and you want to talk about volumes of structures. Well, the way scientists model those coronal mass ejections coming off from the sun is with a cone. And we need to know how much material is in that cone. And so figuring out the volume of that cone, it's a lot more interesting than just seeing a diagram on a page when you're trying to predict space weather, whether or not your astronaut is going to survive because of this event. So we have those materials. We're providing them to learners of all ages, really, but our target audience is grades 5 through 12 with a little bit of spillover on either end. So if you're if you're an educator, or if you are an undergraduate, or you're in community college, this is the stuff for you. This is really trying to connect what you're learning to something tangible, something real, and something that's honestly a lot more engaging than staring at numbers on a page or just learning a bland concept. So I'm already sold, right? Like, I already know that the sun is amazing. I already think that the sun is something that not only teaches us about our place in the solar system, but gives us insight into how life exists, how physics exists, how the universe exists. Like, the sun is this place that we can look to for a lot of these questions, and we can get a lot of answers out of it. It's a fascinating thing, and that's what he's trying to do, is help people understand. I think the tagline we came up with is to humanize heliophysics. So we're trying to get you connected to your sun.
we'll make sure we put in the description of the video, we'll make sure we put the link. So people don't have to hunt for it. They can go right to it from the description. Make it a little easier on them.
Yeah, please do. And so we're part of a larger cohort at NASA called Science Activation. So Science Activation is many different programs across the country looking to bring NASA into the classroom and into your community. And so this is really the outreach arm of a lot of NASA science. So there are many different programs there, some related to the eclipse, some related to Earth science, some related to astrophysics. So especially if you're an educator or if you're just a curious individual and want to get in touch with NASA in your backyard, the Science Activation Network is a great way to access that. And then we can provide the link for that as well.
Yes, definitely. Because that's okay. A lot of our people are science teachers and students that watch our videos, but we also have just a lot of science enthusiasts. And so I love that you mentioned just if you just want to know more about how the science there, because a lot of people are curious. I mean, I know myself, we talk about different things and I have no choice. I am driven to go look up a little bit more about that because it's exciting. And so a lot of people, I think, appreciate the fact that the sites like that are there, that we can go get science from the experts.
Absolutely. And I think that's very key, right? Science from the experts, a reliable source of information that you can count on. So that's good.
And especially especially if you want to be a volunteer, there are ways that you can be a volunteer officially. Like if you want to be a solar system ambassador, you can be a science nerd that is recognized by NASA. And so you can join the Solar System Ambassador Program. It's a fantastic program run through SciAc to really engage your community on all sorts of astronomy topics. If you are an undergraduate or if you are late high school and you want to specifically get engaged with the eclipse, the Eclipse Ambassadors program that's run under SciAc, that is recruiting people right now to be eclipse ambassadors in your community. So if you have any listeners out there that maybe are an enthusiast themselves or know of one that is a younger person that is enthusiastic and eager to engage your community about the eclipse Ambassadors is a fantastic program. So it's not just about getting information, but it's also about volunteering and giving back to your community with NASA's help.
Oh, that's awesome.
That is.
I like that. Well, this is awesome. We really appreciate you taking time chatting with us, and we'll definitely follow up and see if we can't get more of your coworkers to talk about some of those topics, because I know the listeners and the teachers and science enthusiasts, heck, who doesn't want to know? So, thank you.
I feel like this just flew. I mean, I was just eating every word he said. I thought, gosh, this is wonderful.
Well, I'm really glad, because I think for so long the sun has just been sort of background, like it's your weather. Are you looking if it's sunny or out? And I'm here to tell you that the sun's so much more exciting about that. So I'm happy to answer your questions, and I'm also happy to come back on here if you get questions from your listening audience and you want me to readdress some things. I'm happy to come back and talk through some more stuff.
Oh, that's fair.
Thank you so much. Thank you for listening to this episode of Science from the Experts from Purdue University Superheroes of Science.
If you like this episode, subscribe, give us a positive review, and share the love. Boiler up!
Hammer down.